the July Plenary Colloquium organized by the Italian Society of Statistical Physics. And the speaker of this afternoon is Professor Keiji Saito, who is Professor of Theoretical Physics at the University of Keio in Japan. He is a very renowned authority at the international level in the fields of non-equilibrium statistical physics, transport phenomena, and quantum dynamics. And his main scientific contributions are quite well known and concern non-equilibrium fluctuations, thermodynamics structure, and non-equilibrium phenomena in mesoscopic systems. And his work is mainly inspired by a statistical mechanics approach to the study of these mesoscopic problems of heat and charge transport. So it's clear that these latter topics inspired what he is going to present in this plenary colloquium, which are certainly arguments of very great interest for all of our community, and in particular, I should stress to me that I've been working in this field for many years with other colleagues. And let me just again warmly thank Professor Saito for having accepted our invitation, and in particular for presenting his plenary colloquium at this unusual time, which is imposed by the time zone difference between Italy and Japan. But it seems that nowadays these distances can be covered easily, and we have the opportunity of hearing nice talk. Thank you, Keiji, and then please.
Thank you very much. Thank you very much, Robert. And so I'm Keiji Saito from Japan. Now it's evening here and getting dark. And in Italy, it's time is 12 o'clock, lunchtime. So listen to my seminar, having lunch. So okay, let me start a seminar. And first of all, I'd like to thank Robert and Marco for inviting this nice seminar. So my title is here. Microscopic theory of fluctuating hydrodynamics in nonlinear lattices. And I welcome your question, and please don't hesitate interrupting my talk when you have questions at any time. Okay, so let me start with very general things. That is a hierarchical structure depending on the scale of hydrodynamics. In my talk, I do not discuss quantum mechanics, but discuss only classical mechanics. So let's think of the system that consists of a huge number of particles. At microscopic level, each particle obeys a deterministic dynamics by Newton equation like this. On the other hand, if you look at the system at macroscopic level, you can see only the flow of conserved quantity. The velocity field B obeys a famous Navier-Stokes equation like this. As you know, this equation provides a robust and effective dynamics at the macroscopic level. So what happens in between? Namely the mesoscopic scale. If we look at the system very carefully, the particle motion may be able to see, but the overall structure is almost the same as macroscopic level hydrodynamics. In this mesoscopic scale, it is known that fluctuating hydrodynamics provides an effective dynamics. In the fluctuating hydrodynamics, the left is given by this equation. And in the fluctuating hydrodynamics, left-hand side is the same as in the Navier-Stokes equation. More precisely, this is the Euler equation. In the right-hand side, we put two terms. This term is viscosity, which is called Baire transport coefficient. The amplitude of Baire transport coefficient nu0 is not necessarily equal to the nu in the macroscopic scale. In general, this and this are different from each other. in addition, we put the noise by hand. Noise and Baire transport coefficient are connected to each other by fluctuating dissipation theorem like this. Then fluctuation dissipation theorem guarantees the thermalization, namely the equilibrium distribution at a steady state is equilibrium distribution. Okay, so this is a rough. Yes.
Yes, can I ask you a question to you before? Because I do remember some papers by Koplik and collaborators that they've shown that the Navier-Stokes equation as such is valid, on the huge, the difference in length scale from astronomical length scale to microscopic, very microscopic length scale. So I was wondering, if there is really a limiting, when you talk about the mesoscopic scale, you're talking about which length scale? This was.
Okay, that's actually mesoscopic is a big, big words about mesoscopic. Macroscopic and microscopic is relatively clear. And mesoscopic, yeah, actually. Yeah, actually, this fluctuating hydrodynamics always satisfied, always exist. And the macroscopic level, all transport coefficient must be renormalized. Then we get the Navier-Stokes equation at macroscopic level. And yeah, actually, this scale is vague, quite vague. Sorry. Actually, I don't know the answer, clear answer.
This one I'm asking is because the way in which they show is really by molecular dynamics. So they show that using molecular dynamics and mapping to and matching with the Navier-Stokes equation, they show that these were old papers. So maybe there are updates on that, but they show that probably the Navier-Stokes equation is the one that has the largest validity, of all physics, so I was wondering. Okay, so but this was just a curiosity. Sorry for having interrupted you, but I thought it was relevant.
Yes. Navier-Stokes equation is quite robust, and in higher dimension. We don't take account of noises here, and Navier-Stokes equation is robust. So in my talk, I talk about the low dimension system, and this type and this type must be discriminated.
Okay, thank you.
Okay, thank you for questions.
Keiji,
yes.
I would say that in some sense, the answer to the question of Achille Giacometti is inherent to the very equation, because essentially is what you are saying just now. So I'm sure that in some sense the Navier-Stokes is macroscopic because you can get rid of noise, while at the mesoscopic level, noise is a crucial ingredient, as you were saying, and that's exactly is the size of fluctuations, of noisy fluctuations, which matters this kind of behavior. So, I mean, as you were saying, there is a relation between the nu naught and the length scale, if you want, or a time scale, which is related to the transport properties in this kind of system, which are ruled by noise rather than average or renormalized at the macroscopic level. Okay, so there is a way to specify something, but it's model dependent also in some sense. It depends very much on which kind of system you are trying to describe. This is at least my point of view on this.
Yes,
sorry.
I agree.
Exactly.
I agree. Yes, thank you, Roberto. I agree.
Yes. Okay, thank you very much for follow up my talk. Very nice. Okay, so let me again review on the property of the fluctuating hydrodynamics. Actually, the equation is given in the famous Landau-Lifshitz textbooks on fluid mechanics, and so you can see the textbook if we want later. As I said, the fluctuating hydrodynamics consists of Euler equation, Euler term, that is a flow term, and its reversible term. In addition to this, it has a dissipative part, irreversible part, consisting of Baire transport coefficient and noises. So this equation stands for the mesoscopic dynamics, where the noise effect is significant, and it's a hybrid dynamics. It contains the Euler equation and Langevin type of noise. And Baire transport coefficient and noises are usually put by hand to guarantee the thermalization, and these terms are connected to each other by a fluctuating dispersion theorem. These are rough properties that fluctuating hydrodynamics has. So below, I'd like to show you the several things, two things. The first one is how to construct dissipative part in phenomenological way. It's quite easy. And second one is to explain several properties, several successful story where fluctuating hydrodynamics derives non-trivial physical phenomena. Actually, the fluctuating hydrodynamics can derive non-trivial phenomena. Okay, so let's explain about this and this. First, I explain how to construct the irreversible term, dissipative term, using a simple example. To this end, we need to note that hydrodynamics is effective dynamics for conserved quantity. This is quite crucial. So we need to find a conserved quantity for a given system. Suppose that we have a system where only energy is conserved and no Euler term. Let epsilon xt be an energy field at the position x and time t. Because the energy is conserved, this guy should obey the continuity equation using the energy current J. In addition, from Onsanga's argument, dissipative current. Now this is dissipative current. Dissipative current is driven by the conjugate variable to the conserved quantity. So in this case, the conjugate variable to energy is inverse temperature, beta. So you can write in this way. Plugging this equation into this, then we have the equation like this. At this level, we go to the next step. At the next step, we put noise by hand like this for the current part. And we impose the fluctuation dispersion theorem like this. This and noise is connected to each other. Then, finally, at the moment this equation is not closed with respect to energy. I want to make a closed equation with respect to energy. Then, energy and variable have to be connected to each other. In this case, energy and inverse temperature. These two are should be connected by a specific heat like this. Then plugging this to this, we finally get this type of fluctuating hydrodynamics. So here, this kappa over c is a Baire transport coefficient. So this is a very easy derivation about the dissipative part. So next, let me explain several examples where the fluctuating hydrodynamics can derive non-trivial phenomena. First example is non-equilibrium correlation. This is a review for this. And suppose that we have one-dimensional heat conductor and the heat conductor is attached to left and right reservoirs. And if this thermal reservoir have the same temperature T, then the system will be in equilibrium. As you know, unless the system has phase transition, when the two-point correlation function, spatial correlation function for different positions should decay exponentially. When x and x prime are sufficiently far from each other, one can say that no correlation exists, like this. So the question is, what happens in non-equilibrium situation? We put different temperature here. In the left reservoir, we put the additional temperature delta T. Because of different temperature, finite heat flows. And to consider correlation for the energy, it's nice to use of fluctuating hydrodynamics that we derived in the previous page. The energy and the temperature is more or less the same because these are connected by specific heat. We can set boundary condition here and here for energy field. And then we can average over the noise to calculate this. Good thing is about fluctuating hydrodynamics in this case is that the equation is linear equation. So everything is computable. And it's easy to derive the steady state correlation function, actually. The calculation is quite easy, a level of exercise of students. Here I show the schematic graph for the correlation as a function of x prime for fixed x. So the y-axis is the correlation. And as you see, the correlation shows a peak at x equal x prime, and otherwise this shows the power of decay. This is a highly non-trivial phenomenon that's caused by the non-equilibrium situation. And suppose that the conductor is a nonlinear system like this, then it's easy to compute numerically about this stuff, this function. And for heat reservoir, we use Rajban dynamics, and we can confirm that this type of spatial correlation really exists. The important thing is that computer simulation is a bit very difficult, time consuming, and average is very difficult. We must use the many samples. But using the fluctuating hydrodynamics, it's easy to derive this non-trivial phenomenon. This is one of the success. So, okay, this is the first example that fluctuating hydrodynamics can predict non-trivial phenomenon. And I'd like to show you another non-trivial example. And this is a famous application of famous anomalous transport in low-dimensional systems. This was to consider anomalous transport in low-dimensional system. Felster, Nelson, Stefan used fluctuating hydrodynamics to explain the phenomenon. So this paper is many years back, 1977. Before their paper, a famous paper by Alder Weinland exists. Alder and Weinland performed numerical calculation to calculate the velocity-velocity correlation. Surprisingly, they found that autocorrelation function of velocity decay in power law form. From this expression, one dimension and two dimensions shows anomalous diffusion, which implies the divergence of diffusion. Felster, Nelson, Stefan used fluctuating hydrodynamics that explained before. Using the dynamical renormalization group analysis, they showed the anomaly in low dimensions. which looks like this for especially for two-dimensional system for small wave number and small frequency. This is another important result predicted by fluctuating hydrodynamics. So another similar example is on anomalous heat transport. Actually, in today's talk, I explain our work using this phenomenon. So to this end, I need to explain what anomalous heat transport is. Anomalous heat transport is a similar phenomenon to anomalous particle diffusion, but here it's on heat transport. This was numerically discovered by Italian physicists Libri and Politi, as you know. Just in case, I'd like to explain what the phenomenon is. Suppose that we have one-dimensional heat conductor. The Hamiltonian is given by this kinetic term and spinning potential, which connects nearest neighbor particles. Then we want to know the heat conductivity in macroscopic scale. The conductivity can be computed by Green-Kubo formula, as you know. In the formula, of course, we need to be careful on the order. Namely, we first take the infinite size first, and next we take the infinite time next. Surprisingly, autocorrelation function for total heat current decays in power law form, and exponent A is between 0 and 1. You can demonstrate this fact using the numerical calculation using some potential, spin potential. As you see at the long time tail, at long time behavior, you can see the clear power law behavior. So because exponent A is between 0 and 1, Kubo formula shows the divergent heat conductivity. So this is the anomalous heat transport. This is actually counterintuitive result since we have never seen this phenomenon in our daily life. Because our daily life composed of the higher dimensional systems. And in addition to this, the mechanism does not use any quantum effect and any phase transition and so on. So I can say that it is quite counterintuitive. And precisely speaking, the one-dimensional macroscopic physical object is impossible to make because of a lot of thermal fluctuation. We cannot connect the Earth and the Moon by truly one-dimensional physical object. In this sense, true divergence cannot be seen. Nevertheless, recent experiment shows some indication of divergence. In this experiment, they use carbon nanotube. Carbon nanotube is a quasi one-dimensional physical object, and in this paper, they make up to 2 mm size of carbon nanotube. It's a huge compared to the standard carbon nanotube. Using this, they calculated the size dependence of heat conductivity, and as you see, there is an indication of divergence of the heat conductivity. This is a surprising indication. So this is the explanation of anomalous heat transport. So now we turn to the fluctuating hydrodynamics. In 2013 and 2014, Hailbelt Approach, who is a German mathematical physicist, used fluctuating hydrodynamics to explain the anomalous heat transport. Here I explain the rough structure of fluctuating hydrodynamics that he used. I do not explain the detailed calculation. The one-dimensional object generally has 3 conserved quantities, as long as the system is a non-integrable system. Because we fix the total length, total length is conserved quantity. Total length is always constant in the dynamics. And another conserved quantity is momentum, and the third quantity is energy. Without showing the details, he used the hydrodynamics for these three conserved quantity. Concerning the R variable, I will explain later. Calligraphy J is a part of Euler current, and this part is a dissipative part. Euler current. Concerning the Euler current, I don't explain the detailed structure. I just put the symbol here. So it's not essential to Euler current. What is most important here is that he put finite Baire transport coefficient. D is a finite Baire transport coefficient and noises. Assuming the finite Baire transport coefficient, he showed a diverging macroscopic transport coefficient. For instance, d epsilon epsilon, these are kind of transport coefficient with respect to energy. In macroscopic picture, this term is directly related to the macroscopic heat transport. Here, this equation is regarded as a mesoscopic equation, and then we assume that these are finite. In his calculation, finite Baire transport coefficient and noise property are crucial to derive diverging heat conductivity. So we can say that finite Baire transport coefficient in mesoscopic level leads to diverging macroscopic transport coefficient. This is rather impressive structure. Okay, is it okay? Okay, so this is a symbolically nice. Yeah.
It's okay. Okay, I have no questions, so at least I know about this story, but
okay.
I do think that many people.
Yes, okay. Thank you very much. So this is a nice structure. Microscopic finite Baire transport coefficient derives diverging transport coefficient. So the natural question is the following. What is the origin of the Baire transport coefficient? The questions are, how does the stochastic term appear? And why can the Baire transport coefficient be finite while macroscopic transport diverges? This is a counterintuitive. Why these two are competitive? This is a deep question. Because this is a deep question, so there are several papers on these topics. For instance, Fujisaka, very famous papers, and Morozov and Zubalev also have a paper about this. However, these papers are very abstract and cannot judge the validity actually. So we decided to reconsider these questions. Now we have many papers on diverging heat conductivity from numerical calculations and mathematical analysis and so on. So we can accurately discuss the origin of the Baire transport coefficient in many angles, including numerical calculation. So it's nice time to discuss this question again. Concerning this question, we have one remark. In case of Brownian motion, the Brownian motion, the Langemann dynamics has noises here. The origin of noise is given by external environment. By integrating out the degree of freedom with respect to external environment, we can derive the Brownian dynamics, including the noise. But our system is isolated system that is not attached to any external environment. So the origin of noises should be very different from the Brownian motion. This is one remark. So now let me talk on our work. We consider classical nonlinear lattices. Hamilton is given by this. And the first term is a kinetic term, and this is a spring potential connecting the nearest neighbor particles. And the keywords to derive hydrodynamics are mainly three things. The first keyword is coarse-graining in space. The second keyword is projection of the dynamics onto the conserved quantity. So up to here, rather standard, I guess. But another relatively new keyword is ensemble equivalence between microscopic ensemble and Gibbs ensemble. We use the GGE, generalized Gibbs ensemble, because we have the three conserved quantity, not only the energy, but also several other quantity exist. So we use the terminology, generalized Gibbs ensemble. So or you can use the terminology of large deviation. This keyword is also important. So let me start with checking the conserved quantity. As I said already, before, the system has three conserved quantities: the length, and the momentum, and energy. And for microscopic local variable for length, we introduce a stretch, which is a deviation of the position between the nearest neighbor. The summation over the stretch is constant. We fix the total length L, and the summation over this equals to L. And momentum is also conserved, and energy is conserved. The one remark is about the stretch variable. In the standard hydrodynamics, we usually take the mass as a conserved quantity instead of stretch variable. But those are more or less the same. We can switch the stretch variable to mass variable and vice versa. So mathematically, this easy to this variable is suitable to calculate. Okay, so as I said, we have three keywords to derive the hydrodynamics, and using the three keywords, I derived the fluctuating hydrodynamics step by step. So we first use first keyword, which is coarse-graining in space. Coarse-graining in space. Sorry. Okay. The original coordinate of the particle was n, but now we introduce a new coordinate x, as assigning a unit cell for every L particle. In this example, we use L equal 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Every L particle we assign the coordinate x. In addition, we introduce a coarse-graining for conserved quantities. We use the terminology U hat that depends on A and X. If A equals R, this is a coarse-graining variable for a stretch variable. If A equals P, this is a coarse-graining variable for momentum. If A equals epsilon, this means a coarse-grained energy in this block, in this new coordinate. For coarse-graining for a stretch variable, we define this way using the difference of center of mass of the center of mass of nearest blocks, x and x prime. This is the center of mass. For A equals P, which is about the momentum, coarse-graining momentum is defined as the average of momentum in the X block. Similarly, A equals epsilon, which is the energy part, coarse-graining energy is defined as the average of energy in the X block. In this way, we introduce the coarse-grained variable. Here, hat, we put hat hat means the variable depends on the phase space. Namely, once phase space determined, once phase space is assigned, detailed quantity is determined. For instance, we have phase space like this. Suppose we have Q1 equal 1 and P1 equal 1 and P1 hat. If you write P1 hat, then this produce 1. This kind like this, the hat means hat is a variable, phase space dependent variable. So please keep in mind in this terminology. And if you write just UAX without hat, then this is a C number variable. Okay, so I have one remark about the coarse-grained variable, because the summation of coarse-grained variable over X is again constant. Again constant. This means that coarse-grained variable are again conserved quantity. I hope it's clear. So let me go to next slide. And so so because the coarse-grained variable is also conserved quantity, continuity equation should exist like this, even for the coarse-grained variable. And J is a coarse-grained current. And because we set the variable, coarse-grained variable here and here and here, then this current is defined at the border between the different block. X is defined like here. This is a structure. Okay, so next, let me explain about the projection.
Sorry, I have just a very short remark. In the previous slide, you were writing the current, but it's clear that this coarse-grained current is a function of the coarse-grained variables. Am I correct?
It's not obvious. In general, it's not a function of coarse-grained current.
It's not a function of the coarse-grained variable? I mean, the coarse-grained.
In general, actually, only. Okay,
so you cannot J hat as a function of Q P hat and epsilon hat?
Only coarse-grained current for momentum is given by the coarse-grained variable. This no. Such variable. Rx is only given by coarse-grained variable UPX. Otherwise JPX and J epsilon x is not the function of coarse-grained variable. This is a microscopic. Actually, you can write the expression microscopically. This is a function of Rn Pn plus 1. Sorry, no. Pn with dash Rn like this, and n is a border, very local variable.
Okay. So you adopt the definition to definition concerning the properties of the non-coarse-grained variables at the boundaries of the cells. Okay. Yes. No, I understand. But okay, but this is well, okay. I understand. Okay, sorry.
Thank you very much for question. It's quite important. I said the current is a local variable, but the coarse-grained variable is a kind of macroscopic variable when L is sufficiently large. So this structure is quite important. So thank you very much. And only the stretch current is given by the coarse-grained variable like this. Because of this, we can write because of this, time evolution for a stretch variable is deterministic.
Yes,
because of this, for this we have no noise.
Yeah, but you have noise in the other ones because you have to take care about the boundary definition. I see. Okay.
Yes.
Yes.
Thank you very much for nice comment. Okay, so next I introduce the projection. I need to hurry up. As I mentioned, phase space in the previous page. In our formulation, we fix the total length and imposing a periodic boundary condition for stretch and momentum, namely the this and this. Then the phase space is described by stretch and momentum, not the position and momentum. Using this periodic boundary condition, phase space given by the stretch variable and momentum variable. Now we introduce a projection. Suppose that we consider any phase space dependent function A. Original function A is a function of the details of the phase space. But suppose that we know the information only from the coarse-grained conserved quantities. In this situation, it's natural to write the function A in terms of conserved quantities. A in terms of the information of coarse-grained. A is originally the phase space dependent variable. In mathematical level, this type of projection is formulated like this. Integration over gamma prime means the phase space integration with respect to gamma prime. For a given phase space gamma, the set of coarse-grained conserved quantity are uniquely determined. As I said, we assume that we can see only the coarse-grained variable. So we pick up the phase space so that the coarse-grained variable U gamma prime is equal to the U gamma. The omega is the phase space volume where U gamma prime is equal to U gamma. In this way, any function A is projected onto a coarse-grained conserved quantity. This is introduced by Zwandi in 1961 in slightly different context. We used his idea to derive fluctuating hydrodynamics. So let me repeat the expression in different way. For given gamma, different phase space originally generates different value in the function A. But if this regime, for example, in this regime, the coarse-grained variable has the same value, then we also assign the same value for A. This is what this projection doing. Everything is determined through the coarse-grained conserved quantities. And it is straightforward to check that this operator is a projection, namely it satisfies p squared equal to p. We notice that through this procedure, we lose information of phase space. Through the information loss, irreversibility appears. This is the story. So as I said, there is an information loss in the projection. The details of the phase space behind the coarse-grained conserved quantities are hidden. Having this in mind, we consider the time evolution of distribution of coarse-grained conserved quantities. As I said, hat means the variable depends on the phase space. But variable without hat is a C number. And rho t, let rho t be a whole distribution depending on the phase space. And this obeys the Libri equation like this. Using the whole distribution, we can define the distribution that coarse-grained conserved quantity hat u takes the C number values u. This is the exact definition of the distribution of the conserved coarse-grained variable. At mathematical level, this distribution has a similar structure to the projection, and so we can use the technique of projection operator method. By taking derivative for the distribution with respect to time, we have this equation, and we divide rho into two parts, projection part and 1 minus p projection part. After some approximation using Markovian approximation and so on, we have the following Fokker-Planck equation. The details of each term will be addressed later. Important thing is that projection part generates this expression, and this expression is the Euler current, corresponds to the Euler current. And 1 minus p projection derives the dissipative part, irreversible part. As I said, because of the information loss, the irreversibility appears. So now we want to consider the Langevin equation corresponding to this Fokker-Planck equation. The question is the inverse to the standard setup. Usually we have the Langevin equation first, and we derive the Fokker-Planck equation. Now we have the Fokker-Planck equation first, and we want to identify the corresponding Langevin equation. So in this sense, the method is a kind of inverse. For instance, as you know, for instance, usually we start with the Langevin equation and we derive the Fokker-Planck equation like this. But we want to go inverse way, opposite way. We know Fokker-Planck equation that I derived in the previous page, and we want to know the corresponding Langevin equation. So in fact, mathematically, we don't know the uniqueness, but we can show that this Langevin type equation can derive the Fokker-Planck equation in the previous page, and it's consistent. The here variable lambda is a conjugate variable to the conserved quantity. If A coefficient, the conserved quantity is the energy, and so the conjugate variable should be an inverse temperature in this case. The conjugate variable lambda is usually connected to the local conserved quantity like this. Then eventually we get the closed fluctuating hydrodynamics like this. Here K is a Baire transport coefficient, and this part is a Euler current. I explain later about the detail.
Sorry,
this part and this part.
I have a question. When you derive from the Fokker-Planck the corresponding Langevin equation, the relation that you write for the noise is correct, but you have to assume that fluctuation dissipation holds true.
Yes. This
otherwise,
this
cannot KAA cannot be anything. It must be something very specific. Otherwise, so in some senses you have to impose by hand.
Yes. This is imposed by hand. Yes.
Okay, no, it's
but
correct.
very natural. Yes, because the first dynamics, determinist dynamics, exact derivation is impossible in general. But at some point we need some approximation and assumption. This is the case. This is always the case in the deriving the hydrodynamics.
I agree.
So in this case,
I totally agree with you. But you have to put it by hand. So nobody tells you that should be real, the correct dissipation, fluctuation dissipation relation. If you have not the right coefficient, you are violating it. So you put it in such a way that dissipation fluctuation holds true. Or is that okay?
Yes.
Fine.
Yes, exactly. Yes, thank you very much. So without the fluctuation dissipation theorem, we cannot reproduce the Fokker-Planck equation. So we impose by hand fluctuation dissipation theorem. Then we get the fluctuation dissipation, the Fokker-Planck equation in the previous page. Okay, so thank you very much. Okay, so and so this part is Euler current, and this part is a Baire transport coefficient, and this Baire transport coefficient is given by a Green-Kubo-like formula, like this. Here Q is a 1 minus P projection. This means that subtraction P times current must be included. This is very different from the standard Green-Kubo formula. Okay, this is a rough story to reach the fluctuating hydrodynamics. I skipped the details, sorry for this, but this is a rough story. Okay, so let me go to the final last stage. Next, we explain how to calculate the Euler term, and also Baire transport coefficient. First, we consider the Euler current, Euler term. We use the terminology local equilibrium current for the Euler current. This term can be calculated using the following the local microcanonical distribution. In the local microcanonical ensemble, we assign C number U A prime X for the X block. And we consider all phase space satisfying the coarse-graining conserved quantities are equal to the value U. So in this sense, the locally microcanonical ensemble are defined. So now we use the standard statistical physics concept, namely the ensemble equivalence. For sufficiently large system, large volume, we are allowed to replace a microcanonical ensemble by Gibbs state. In this case, we apply ensemble equivalence for every X step, X block. For instance, if the conserved quantity is only energy, the microcanonical ensemble is equivalent to the canonical ensemble with a corresponding inverse temperature. In this case, conjugate variable lambda depends on the local block, which means a local equilibrium picture. We impose a condition that Gibbs state equal X. We impose this condition, then the lambda is regarded as a function of U. Using this condition, we can systematically calculate the Euler current like this. And in terms of the given U, we can expand like this. Actually, this is exactly the same expression as Hailbelt used in his paper. Like this, Hailbelt's treatment are justified microscopically. And finally, I explained the structure in calculating the Baire transport coefficient. As I said, the Baire transport coefficient is given by the Green-Kubo-like formula. Green-Kubo-like formula JQ T QJ. This type of calculation is necessary, and Q is 1 minus P. So we need to calculate the projection of the current. So So to calculate the Green-Kubo formula, we need a computable expression of the projection. This is a mathematical expression for the projection. And this is a mathematical expression for the projection. In fact, this is completely the same mathematical structure as in Euler current, except that this case contains phase space. In previous case, this is the C number, but we put the phase space dependent variable. And so for given phase space, we assign U gamma for each block. Otherwise, the structure is completely the same as in the Euler current. This means that if coarse-graining length L is sufficiently large, then we again use the ensemble equivalence technique. Using this ensemble equivalence technique, so now the conjugate variable lambda depends on the phase space. Using this technique, we again expanded the projected current in this way, and A and H and so on. These coefficients are the same as in the Euler's current. So, sorry for the bad explanation. So, so using this technique, we can accurately consider the Baire transport coefficient as long as the coarse-graining length L is sufficiently large. To demonstrate that the Baire transport coefficient is computable and the Baire transport coefficient is eventually saturated, we use a prototype nonlinear lattice. That is a FPU Fermi-Pastor-Ram-Zungo model, which is a standard model to consider anomalous heat transport. Most interesting component is energy-energy correlation. Because the macroscopic correlations for energy-energy current shows the power of behavior at long time. Now we use a coarse-grained correlation, which has a subtraction structure. And we consider the size dependence and the coarse-graining length dependence. So the result looks like this. X-axis is the coarse-graining length L. As you see, for sufficiently large system size N, the results are the same for fixed L. The blue cross and the red is the same for the fixed L. And the y-axis is the integrated correlation function. And if it's saturated, this shows the Baire transport coefficient. Important thing is that for sufficiently large coarse-graining lengths, the Baire transport coefficient converges the same value. This means that sufficiently large coarse-graining lengths, the Baire transport coefficient is uniquely determined. This means each material have each unique values on Baire transport coefficient. This is a message given by numerical calculation. Okay, so time is almost up, so let me summarize my talk. So as I explained, finite Baire transport coefficient is used to derive the diverging heat conductivity. So with this motivation, Baire transport coefficient is addressed. And several keywords are important. First, coarse-graining in space and projection onto the conserved quantity. And projection onto the conserved quantity is a kind of coarse-graining in time because the conserved quantity behaves very slowly. So these are both coarse-graining. This is the space, coarse-graining in space, and this is a coarse-graining in time, in a sense. And in addition to this, we introduce the ensemble equivalence to make everything computable. And using the technique, we can demonstrate that the Baire transport coefficient is saturated for sufficiently large coarse-graining length L. And you can summarize the formula for coarse-graining length here. So first we take size infinity, and next we take the coarse-graining length infinity. Then we get the finite inherent values in the material. Okay, this is a message from my side, and thank you very much for attention.
Thank you very much, Keiji. It was a really nice seminar. It was really interesting, and we have appreciated the details of our approach, because reading paper is not the same as listening to someone is going to explain the main points.
Yes.
And
yes.
say that's a very, very important step forward in all this field, and it clarifies a lot, many aspects of the problem at hand. And I think that your effort was really very, very interesting and nice, and now I understand much better.
Thank you very much.
Your point about pair transport coefficients. Now, okay, I am on the other hand in more or less in the field, as you were mentioning before, so it's not a big surprise to me, but anyway, I find it very, very illuminating. Thank you very much. So,
you're welcome.
Are there any questions? By the way, I have a very short question for you.
Yeah.
Probably you certainly know that Henk van Buren in 2014 tried to approach this problem using a similar projection technique, but which is not the one you showed us, relying upon a different technique, which is mode coupling theory, which is, you know,
yes.
a hydrodynamic normalization method, which is not exactly equivalent, technically speaking, to what you are explaining to us, which certainly is much more, how to say, refined and clear from a mathematical point of view. Anyway, by that approach, it was he was able to, and also Hailbelt in a similar way, to show that the overall problem of the Fermi-Pascal single problem enters the universality class of KPZ-like behavior, which is essentially what comes out of all this story, and which is also inherent, is written inside your approach. So you probably, did you make a bridge between these kind of approaches, or is it easy to be performed? Certainly it exists, but...
Okay, so first, concerning the Hailbelt approach, I completely reproduce his approach using this technique. And his starting point was fluctuating hydrodynamics. But Henk's approach somewhat different from this. And so at the moment, it's not clear for me about this.
Well, it would be interesting to discuss this privately, because it's there is something very interesting behind this story, and we'll discuss for hopefully in the next future. Thank you.
Yes, thank you. Yes.
So if there are any other questions, I will thank again Professor Saito for his very nice and illuminating talk, and thank you very much, and I hope to see you soon, maybe in Japan or online in the next future.
Yeah,
bye.
In Japan we have SIFS conference. Thank you very much for inviting the nice conversation. Bye. Thank you very much.